Welcome back. This is the second part of Chapter 5. In this one we're going to focus primarily on lipids. I'd like to recall the processes of dehydration and hydrolysis in regards to creating polymers from monomers to form our macromolecules. Now lipids are another word for fats. So fats, lipids, same thing, and they're constructed from two smaller molecules. The first being glycerol and the second being fatty acids. We can see this in the image on the screen here. Glycerol is a 3-carbon alcohol with a hydroxyl group attached to each end of it. And these are attached to the fatty acids. Fatty acids contain a carboxyl group, the COOH, linked to a long chain of carbons and of hydrogens. The fatty acids attach to the glycerol by ester linkages between the hydroxyl and carboxyl groups, which result from dehydration between the two, and we see the dehydration going on right here, removing the water. The bond that results from the dehydration is called an ester linkage. Triaglycerol, or triglycerides as we commonly know them, are when 3 fatty acids form ester linkages with glycerol. We see this going on here in the bottom image. The fatty acids in the image show them all to be to be all of the same length, but this is not always the case. Some of these fatty acids, they're longer than others. We can see that they're all the same length here though. So some other tidbits we need to be aware of with lipids before we proceed. First off, lipids do not include true polymers. They're more of a compound between the fatty acids and the glycerol. And they also are hydrophobic. We spoke about hydrophilic previously, water-loving, and hydrophobic being water-fearing. And this is what we see going on when we add lipids or fats such as oil to water. We can see the separation there. And that's because lipids are hydrophobic or nonpolar. This is primarily the result of the hydrocarbons forming nonpolar covalent bonds between the carbons and the hydrogens. The image here shows us the difference between the saturated and unsaturated fats. Saturated fatty acids have the maximum number of hydrogen atoms possible and no double bonds. Unsaturated fatty acids, on the other hand, have one or more double bonds, and we can see those right here. It's a straight line. I'm actually going to go back a slide. You can see a little bit better here. Everywhere there can be a hydrogen attached, there is. That is a saturated fatty acid. It has the maximum number of hydrogens that we can possibly add to this fatty acid. On the other hand, with the unsaturated, we'll have at least one double bond, and that double bond means that there's at least two hydrogen atoms that we have less in this, because this bond is forming here, so we can't have a hydrogen or a hydrogen attached to the 2 carbons now involved. What we see going on here when we have this double bond is an actual bend itself in the molecule, which does change its functionality. Remember that shape fits the function. I guess in this case maybe a better way to think about function would be the properties. One of the properties of the saturated fats is that they are solid at room temperature, such as butter in this case. Also animal fats. Unsaturated, on the other hand, one of their properties is that they're liquid at room temperature, which would be our oils. Now, the general public has a misconception about fats. A lot of people who are not too savvy with health hear the word fats in foods and they think, oh, fats are bad, fats are bad. And that's true to an extent, and that's false to an extent. It really depends. Too much of anything, for one, is bad, but you do need fats. The question is how much of them. Well, the food pyramid, it changed recently, but it used to say, use sparingly. And roughly 30% of your daily caloric intake should be based off fats. What we do need to be aware of, though, are the solid fats, the saturated fats. These ones that you take in from butter or animal fats, they can form plaque deposits in your arteries and veins and lead to cardiovascular disease. And the oils, on the other hand, actually can reduce or minimize the effects of the saturated fats. So you definitely want to have some oils. That's actually healthy for you. Once again, though, too much of it is not going to be good for your health. So use this stuff sparingly, but do make sure that you eat it. Do not avoid it. Other food sources you can get the unsaturated fats from will be plant fats, such as from avocados, which are actually quite high in the unsaturated fats, as well as the fish fats, like your omega-3 fatty acids. That's all referring to this stuff. And if you've heard some of the commercials for some of the foods, they actually promote the omega-3s or the omega-6s because, well, it's good for you. So now that we know a little bit about the saturated and unsaturated fats, let's talk a little bit about the chemistry and things we can do with the unsaturated fats, particularly hydrogenation. This is the process of converting the unsaturated fats to saturated fats, so we can actually change them. We do this by breaking that double bond and adding more hydrogens to fill in the broken bonds. Hydrogenating vegetable oils also creates unsaturated fats with trans double bonds. These trans fats may contribute more than saturated fats to the cardiovascular disease. So you often hear that, no trans fats, no trans fats. A lot of manufacturers and companies and fast food chains are trying to market that and advertise that they do not have these trans fats. The major function of fats is energy storage. We don't typically use them for energy. That's primarily more for carbohydrates. That's what we create ATP from. But when the carbohydrates minimize and they're depleted, we turn to the proteins and fats. And fats pack in 9 calories per gram, so they do contain a lot of energy, but it is not our primary source. We primarily store this stuff as fat or adipose tissue for some of you more savvy anatomy and physiology folks. Next we have phospholipids. Should not be a new term to phospholipids. Pretty common word in biology, as it's part of the double membrane for all cells in our bodies. Phospholipids have 2 fatty acids and a phosphate group, all of which are attached to the glycerol. In this image here we see the glycerol, we have our phosphate group, and then we have our fatty acid tails here. The 2 fatty acid tails are hydrophobic, but the phosphate group and its attachments form a hydrophilic head, which creates a unique property for the phospholipids. It has the top part, which is water-loving, and the bottom tail region, which is water-fearing. So this creates a unique arrangement within the cell membranes. When the phospholipids are added to water, they self-assemble into a bilayer. We'll look at that on the next slide here. This occurs when the hydrophobic tails kind of point towards one another because they're attracted to one another, and the hydrophilic head regions are pointed outwards towards the water because they're attracted to water. So let's check out what this looks like here. We have water outside the cell, water inside the cell, and we have this double layer of phospholipids. And we can see the hydrophilic heads pointing towards the water. Once again, polar is attracted to polar, and also inside the cell, polar head, polar water, they're attracted to one another. The hydrophilic tails, the fatty regions, which are non-polar, they're repelled by the water. Once again, thinking back to the cooking oil mixed with water, they separate. And that's what we see going on here. The non-polar tails from this side arrange themselves with the non-polar tails from the bottom side, which gives us a nice double layer for the cells of our body. The last bit of lipids that we're going to be talking about are steroids. These are characterized by a carbon skeleton consisting of 4 fused rings, and we can see those rings here highlighted in, I guess, yellow. Now the steroid that is probably most important to our body is cholesterol, which you may have heard cholesterol levels. Well, you do need cholesterol. It is an important steroid and is a component in animal cell membranes. So if our bodies have steroids, why would people use anabolic steroids? Well, the reason for that is our bodies don't make the anabolic kind that the muscle builders use. What the anabolic kind do is, well, when you work out, you rip your muscles, and the anabolics actually speed up the healing process. so to speak, to repairing the gaps in the cell membranes as you rip them when you're lifting. And the ripping is what kind of causes your muscles to be sore, with a little bit of acid buildup, of course. However, cholesterol, once again, moderation. High levels of it in the blood may contribute to cardiovascular disease, so you definitely want to be sparing with the amount of cholesterol intake that we have. That concludes our discussion on lipids. The next one we'll be talking about protein.